hear the lecture of Professor Somak Raychaudhury. This is a part of a prelude to the main event, the landing of Chandrayan 2 on the moon, a big achievement which is shortly to arrive for India on 6th night or 7th early morning. As a prelude to that actual landing, Birla Museum has organized a lot of programs. Today we are starting with a lecture. On 2nd, 3rd, 5th and 6th, there will be film festival with a lot of films which we have received from National Geographic. It will be held every day in the morning session in this auditorium. 45 minutes of duration, 10, 11, 12, 3 slots are there for the schools. Lots of schools have already registered for those shows. And on the 6th night, the actual event, when it takes place, it will be shown live in this auditorium as well as in the lawn, provided the monsoon is favor with us. There's a lot of, it doesn't rain outside. So with this word, I request our director, Mr. Raychaudhury, to formally welcome the audience and introduce the speaker. Thank you.
Good morning to one and all. As told by my colleague, I have got a bonanza. That is 7th early morning, 1:40. Vikram is expected to land, soft landing on the moon. I am also very proud to say, Birla Museum is the only center which has got the live feed from ISRO. So it is we made a lot of effort. I could manage with my contacts, and we are going to get live feed. Means there is no delay. It will go on coming, smooth as silk. That is what I can say. Okay. Coming to the topic, it's really a great thing to have such a great astronomer with us, because astronomy is always special. That is the only laboratory which is available every day in the night time. You cannot touch, feel, smell or dissect. You can only see through a telescope or you can send some probe like what you have done to moon and all. So it is a beautiful subject, and we have got a very great personality, and that too the most reputed and very distinguished center, Inter-University Center for Astronomy and Astrophysics. The director is with us. So it is a great honor for all of us. So he is here to talk about Chandrayan 2. And just 4 lines I will tell about Professor Somak Raychaudhury. Professor Somak Raychaudhury, before joining IUCO as director, was associated with the Physics Department, Astrophysics Department of Presidency University, Kolkata, University of Birmingham, University of Smithsonian, and also University of Cambridge. So he is a very distinguished personality, and with a lot of difficulty I got him. And we should be proud he is from Kolkata. That is very, very important actually, such a distinguished gentleman. And we have got a Japanese Vice Consul, Rizwan, Madam is also here. And we have got former Director General, Sri I.K. Mukherjee, who has come all the way. And we have got Dr. Bakshi, and then retired Jagadish Sports Institute Director is also with us. So I don't want to take much time. I want to leave the floor to Somak Raychaudhury. Before that, I would like to welcome you one and all. Without calling by name, I would like to welcome you one and all. Thank you. Please enjoy the lecture. Sit back. After the lecture, there will be question and answer. So thank you. Thanks, sir.
Thank you very much. Thank you, and thank you everybody for coming. A morning like this, we're celebrating, of course, the success so far of India's premier mission. It's the most complicated thing Indian space has attempted. It's also very special for me because Birla Museum, BITM, holds a very special place in my career, in my life. I grew up in Calcutta ever since I was school. And there was a time, I think for many years, starting from a little younger than most of you here, I used to come here every week, if not twice a week. Saturday certainly, and spend the entire time here. And won the science quiz, inter-school science quiz twice. And then later on when I came back as the head of physics at presidency, I also sat on various committees here. At the beginning of the tinkering center upstairs, I participated in quite a lot. I brought my son here to play in the tinkering center. So below is, is one of my second homes. So. I also see some very distinguished people in the audience who have helped me grow. Afyanundi, sitting in the front row. I was a Javing Estes scholar, and then through the Javing Estes program, it really helped me grow as a scientist. I can see Dr. Aishu Mukherjee here, and together with him we worked quite a bit on designing various science exhibits in the early stage of IUCAS. So I'm very happy to see all of you here. Anyway, so before talking about Chandrayan, see, Chandrayan is not something that happened in an isolated sense. I want to put it in the context. And because I am originally a physics teacher, I have to start with some physics. Okay? I hope you don't mind, because the first few minutes of this lecture will be a physics lecture. Because I want you to understand why Chandrayan is so important, even in terms of the mission itself, and how it is different from, say, the NASA missions that went to the moon in the 60s and the 70s. Right. So, what is the main theme here? What we have to do is we have to leave the Earth and go into space. And in particular, then that's not enough. We have to go beyond and go reach the moon. Either we have to build a craft that can reach the moon, orbit the moon, land on the moon. All of this is being done by Chandrayan 2. And at a stage where that is achieved, which the USA achieved in the 60s, Russia achieved in the 60s, then you can send human beings in that craft, and the human beings can land on the moon to do experiments. And that America achieved, as you know, 50 years ago. And so, why are we doing it now? And how is our mission different from that? And what are the main challenges? One of the main challenges is also one of the major advantages we have of physics that holds us onto the Earth. And that is a thing called gravity. And this man called Isaac Newton showed us what gravity is. Right? Gravity holds us on the Earth. If gravity were not there, we would have floated in space. We wouldn't have walked on the Earth, right? And so in order to go to space, you have to break free of gravity. Right? Otherwise, you can jump on the Earth, you come back on the Earth. When I was a little kid, I was very, very afraid if I jumped too hard, I would float away in space. I hope you don't have nightmares like this. You will see that's not easy, and it's not easy, and that is what the main issue here is how to take something and take it out in space. I mean, the whole idea of a rocket that can do this was first conceived by a Russian school teacher more than 100 years ago. After reading Jules Verne's fantasy novel From the Earth to the Moon, people started thinking about how to take rockets in space. I mean, rockets have been used as fireworks, as weapons before. Famous Tipu Sultan rockets used in his war in Karnataka. The rockets used to scare the enemy, rockets used to deliver short-range weapons. Those things have been used before. So people knew about the concept of rockets. And the rocket concept is that you can propel something into space against gravity by using Newton's third law. Right? Now, what you learn in school, simple Newtonian, I'm not going into Einstein, I'm not going into very sophisticated theories of gravity. You know that gravity is a force, and everything in everything in the universe that has mass, you and I have mass, this table has mass, everything has this property that they attract each other. And how do they attract each other? They attract each other with a force that is proportional to the masses of the objects and inversely proportional to the distance. So, and that leads to an acceleration that is proportional to the mass. Say I'm standing on the Earth is pulling me with a force that is proportional to the mass of the Earth, and it's inversely proportional to my distance from the center of the Earth, and that's the R squared thing, this R. Now, in order to go into space, go to the moon, what I need to do is to break free of gravity. How do you do that? What you'd have to do is attain what is known as escape velocity. And to do that, you essentially need a velocity that's strong enough that it has energy, kinetic energy, that overcomes the pull of the Earth due to gravity, the potential energy that it gives. So you can jump, you can throw something up, it will fall to the Earth, and after a certain point, as you increase the velocity, it will attain a certain velocity that it will allow you to take it away from the Earth and overcome the Earth's gravity. And if you do a simple calculation, and I'm sure you have all done this in class, you find that that is given by this very simple expression to Gm over R, where m is the mass of the Earth, or whatever you are trying to escape from, and R is where you are from the center of mass of that thing. And that's not a trivial number. Now, as you increase the mass of this object, this escape velocity increases. You can see from that equation. So, escaping from the moon is easier than escaping from the Earth. Escaping from the sun is even more difficult, right? Of course, there's the R in there as well, but I'm not going to go into that today. That comes in if I talk about black holes. But, so escape is difficult if mass increases, right? And now, so for example, you can escape from the Earth, you can escape from the moon, and as you can see, the escape velocity from the moon is 2.3 kilometers per second, escape from the Earth is 11 kilometers per second. It sounds small, but that 11 kilometers per second is 43,000 kilometers per hour. So you can see that my fear that if I jumped hard enough, I'll escape from the Earth was unfounded. You can't drive that fast. Right? If you drive that fast, the police will catch you. But you can see that the fact that this guy who's trying to walk on the moon is having that funny gait because the gravity is weaker, and so just a small effort makes you go a little more than on the Earth. And you can see that escaping from the moon would be easier for them, but not that easy. You can see that it's just about 6 times or 5 times smaller. So that's like 8,000 kilometers per hour, which is also not something that you can do, right? So one of the things that you have to do is you have to escape the gravity of the Earth. So 7th of September, Chandrayan 2 is going to land on the moon, as you saw, and it is going from the Earth to the moon in this very complicated way. And I want you to understand why. I'm sure a lot of you have already read about it in the papers. Why are we taking 45 days to go to the moon and going in such complicated, very, 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 very complicated orbits, instead of taking off with this escape velocity of root over 2 Gm over R, right? And going from here to here, boom, like that. As you can see that what happened when Chandrayan 2 left the Earth, if you remember, is that it went on an orbit like this. That orbit has slowly been increased, this elliptical nature, increased, these are ellipses, and then now we are in the lunar orbit in about 100 kilometers, going the nearest part, and Chandrayan 2 has started taking pictures and sending pictures of the moon and sending back to us, and I'll show you a few of those. And then slowly that orbit gets smaller and smaller and smaller and gets close, very close, and then a lander lands, right? So that's the whole plan. And I want you to understand, everyone here to understand, why this plan is so complicated. And also, it is not that complicated. It's very simple. It's all governed by the simple Newton's laws of physics that you learned in school. You know that a projectile, if you throw something, it is a parabola, right? So you throw something, and this is something that you've all done in class. Or if you haven't, you will do very soon. That you throw something, a cannonball or a cricket ball or a basketball or whatever, it follows a parabolic trajectory. And that is because in this particular calculation, you assume that the Earth's gravity is parallel, the gravitational pull, and it's constant, right? It's constant over that very small place compared to the large distance to the center of the Earth. The variation here in height is very small, so you can think of it as the constant, that gm over r squared, that r doesn't change much, right? And also, because even though the point here and the point there have a pull that goes directly to the center of the Earth, because it's a very small part of the Earth, you can think of them as parallel. And once you do that, then the trajectory can be thought of as a parabola. It's actually not a parabola. Any orbit that of a point object around another point object actually is not a parabola, but it's actually an ellipse. And that was shown very early on by Newton. So Newton devised his laws to figure out what the shape of this orbit is, because Kepler had, as you know, from the orbit of Mars and orbit of other planets, actually figured out that these things move around the sun in an ellipse, and Newton was trying to, and also Halley's comet was shown to be an ellipse, and Newton was trying to prove that this would result from a form of the gravitational force that goes as gm over r squared, right? And that is how physics came into being. The origin of physics is from that book Newton wrote to explain why planets go around the sun in elliptical orbits. So that's the beginning of all physics. And frankly, it's the beginning of all science as we know it now. And so it's a very important problem. But you also have to understand that this parabola that you see is actually, if you look at, if you start throwing things at higher and higher speeds, finally, if it goes up from the Earth, it will actually go and take an elliptical orbit and come back. Because that's the general form. The parabola is actually a very small part of that ellipse. And that happens because these parabolas and ellipses are all connected. They're all part of a family called conic sections, which is essentially, if you take a cone and you take a section in various ways, you find these very different curves. Okay, so these are very interesting connections that I want you to make as you go along and learn more and more physics in class 11, 12, and learn the mathematics. You will see that these things fall into place. So there's a connection between the trajectory, if you throw something here, and then you throw something in space and it goes into orbit around something. Okay? I want you to understand this because then you understand why it is very important and it takes such a huge bunch of people to engineer a mission like Chandrayan. It's so complicated. And there are some basic things that one needs to control, and you can control it very precisely because they all follow very precise laws of physics. Okay? So eventually, what will happen is that if you have a satellite, it will go around the Earth in an ellipse such that the Earth is at one of the focuses. An ellipse has two focuses or foci, right, which are equidistant from the center of the ellipse. A circle is, as you know, a special case of an ellipse in which these two merge the same. So the Earth or whatever is the center then becomes one of the focuses. Now, if you want to go from the Earth to the Moon, and you don't want to go in one projectile motion, what you have to do is to have to go into orbit around the Earth such that the Earth is in one of the focuses, one of the foci. Right, as you can see. If you can make it a very long ellipse, then the focus shifts to about here. So you can make it into a very long ellipse and stay very close to the Earth and go very far and do that. But every time you increase that size of the ellipse, you have to make sure that the Earth is at the focus. And you can do that. The energetics allow you to do that. All this is part of designing orbits. And so you can see that all these ellipses are, why are they like that? They're not concentric circles. They're not concentric ellipses. They're confocal ellipses, you can say. Because they are in the same way, the Earth is at the focus of all of these ellipses. And you can slowly, by using your engines, you can inject a little more energy into the orbit and go and make it longer and longer. And then you make it into this big orbit. As you can see, the Earth is still at the focus. And then, at some point, you have to transfer it to the moon, such that the moon is at the focus of that ellipse. Right? So you have to do it exactly, and it's a very, very critical, very, very subtle effect that you have to do. So you go exactly with the right kind of velocity near the moon, and the moon says, come, you're mine. So you transfer it, handing the baton over like a relay runner. You become an Earth satellite, and you get transferred to a lunar satellite. Okay? And then you have to do it exactly such that it goes into an orbit which is an ellipse with the moon at the focus. And the mathematics of this is so simple, you can learn this in first year in college. You can do it now. Actually, you know all of it. A little calculus is needed. So maybe a little later, most of you would, when you know calculus, you can do that. But actually, it's very, very simple mathematics. And because it is so simple, it is doable. Right? And it works. So in Chandrayan 2, we are past this point. We belong to the moon. That's already a big achievement, and that has been done. So this, contrast this with what NASA did with the Apollo missions in the 60s. That's what NASA did in 1960. This Apollo 8, Apollo 9, Apollo 11, everyone did the same thing. And what NASA did was that from the Earth to the moon is going around the Earth, it just went around the Earth and boom, boom, slingshot. And it went straight to the moon, and it became captured in the moon. Took 4 days, 4.5 days, done. So they did this, 50 years ago. And that is because even then, America had rockets that was powerful enough that could give you escape velocity straight away. We haven't been able to build such powerful rockets. So I want you to understand that. We feel very proud that India has got to the stage where we can send something to the moon, but our rockets are not powerful. They had the Saturn V, which did this. And Saturn V in those days could take 100 times more payload than we do now. But that hasn't stopped us. And that is why these things cost 50 times more than what our missions cost. So what we are doing is that we're doing it within our means. It's much cheaper, much, much cheaper. But you supplement that with cleverness. Okay. Not 4 days, we take 40 days. But we can design an orbit that is very complicated, and with this very small amount of money, we can reach the moon. Okay? Same effect. Right? But we didn't need to do this boom slingshot, which looks very simple, but costs a lot. I'll talk about the cost a little more. Okay? So that's the basic difference between the Saturn rockets of NASA in the 60s and the GSLV-3 and the PSLV that launched Chandrayan 1, which NASA has deployed. Very clever design, very accurate work. Team of people who are very, very innovative. And we can do it very, very cheap because we can increase their orbit and go there. If you look at NASA's rockets, if you look at these, the Saturn V, which was in the Apollo human missions, if you look at the payload, starting from the early years of NASA, when the payloads they could take 1,000 kilograms, a ton, okay, the early NASA rockets. Titan could take 18,000 kilograms. The Saturn V, Saturn V that took the Apollo missions could take 130,000 kilograms. Okay? And the space shuttle, of course, came on, right? So that's the one that went boom right there. It's a very large, very, very powerful sling. Compare that with ISRO's missions. These are very sophisticated launchers. Of course, we have 50 years of technology which has evolved into lots and lots of more complicated things we can do with these launchers. So we don't need the brute force, very powerful Saturn rockets. But the GSLV Mark III, the payload limit is about 4,000 kilograms, right? 4,000. And we're talking of 129,000, right? So this is why the Saturn rocket could go boom right there. And we have something that's much less powerful but very, very clever. And we can do it in stages and stages and stages and go. That's the basic difference. Right? And this is, of course, the GSLV-3 as cryogenic stages, which they couldn't dream of in those days. And that is why, and I've taken this from very nice graphic that the Times of India produced a few days ago, essentially shows that that how you have to really get to a state with the right velocity, etc., to be captured by the moon. So essentially 22 days in the Earth's orbit, 23rd day, 14th of August, it's transferred to the lunar orbit, and it stays there for about 3 weeks and gets close enough that the lander can land. Whereas the Saturn's thing essentially took 4 days. Right? And then returned absolutely just like that. Slingshot, went circle around the moon, slingshot, one shot came to the Earth. Right? But as a result, what happened was, because it could take 100,000 kilograms of payload or whatever, it could take humans. The GSLV launching our current Chandrayan 2 still is not ready to take humans to the moon. And so it will take a while for us to get there. Now, as it got into the lunar orbit, we are already seeing Chandrayan 2 sending back some very, very interesting images. This is hot from Chandrayan 2, looking at the moon from about 4,000 kilometers above the surface. If you remember, it goes into an orbit in which it will slowly come to a few hundred kilometers. But now, at the beginning, it was inserted into an orbit which goes for a few thousand kilometers, slowly in. This is 23rd of August, about a week after the insertion. And you can already see some of the familiar craters. Now, if you look at the moon and various craters, you can see that these are the places that Apollo landed. The Apollo missions that landed, along with some with humans and some with not. That's of course Apollo 11, the famous, the first human landing was on the equator. And 14, 16, 12, etc. These were all around here. I'm sure you know that we are going to land, Chandrayan 2 is going to land very close to the pole. It's not at the pole, it's 70 degrees latitude. So here's the equator, and it's going to land there, right? So that's 70 degrees latitude, it's going to land there. So people are, if you go on social media, there are a lot of people who are saying, why do they say India is landing on the South Pole? 70 degrees is not the South Pole. It's still 20 degrees from the... But think of a sphere. Sphere, the actual distance between 0 and 10 degrees is much bigger than the distance between 70 degrees. So you can see here, if you look at that, 70 degrees is like that, right? If you look on the Earth, the top of Antarctica is like 65 degrees. Right. The top of Finland is about 70 degrees. So it's 20 degrees from the from the poles. So it is virtually, and we call Antarctica the South Pole, right? It is very, very close to the pole. And I'll tell you in a moment why we want to land there, but it's very far away from the normal landing sites of the NASA missions, the traditional NASA missions. Right? And that's a very important thing for us. One of the science goals of looking for things on the moon is to look at some basic hydrocarbons and to look for water. And we know that there is a much, much bigger chance of getting water, particularly in liquid form, near the poles. And one of the things that we look for is water near the poles. So that's why landing near the pole is very, very important. So, I took this from ISRO's short descriptions of the various components of this mission. And so GSLV Mark III, which a 4-ton class of satellite, and Chandrayan 2 is almost that weight, as I can take it. And it has, the most important thing is that it's got these, the solid rocket boosters and the liquid stage. What happens in a launcher, because it uses Newton's third law, is that it has to ignite a certain fuel, right, which will then cause a thrust in the opposite direction. Newton's third law propels it in one direction. Right? And to do that, one needs to, in order to ignite the fuel, it has to carry oxygen. And it has to carry oxygen in liquid form. So one of the major things that launches like this have to carry is that it has to carry liquid oxygen and has to keep it separate from the liquid hydrogen. And these two are very, very inflammable, as you know, together. And it's a very, very important thing to keep them separate. And one of the things we think happened when the launch was delayed for the first time was that there was an uncertainty as to whether there were some safety issues to do with the liquid fuel. Right. So we use liquid fuel. I'm not going to go into the details of this. The other main component, of course, in Chandrayan 2, that was also there in Chandrayan 1, I'll talk briefly about Chandrayan 1 in a minute, is the orbiter that's going to orbit. That's now orbits the moon. It was orbiting the Earth, and it's now orbiting the moon. It's about 2,400 kilograms. You can see they have to add up to less than 4,000 kilograms for GSLV to be able to launch it. Yeah, and from its own solar power, solar panels, it can generate a kilowatt of electricity, which keeps it going. It's not like there are, any batteries that depend on a certain lifetime. It can actually convert solar power into little storage units in there. The orbiter is expected to last 1 year. Chandrayan 1 actually lasted 2 years, well, a little more than a year. And it eventually has been put into 500 kilometers below the Earth. Now comes the more important bits, which sets it apart from the first lunar mission and makes Chandrayan 2 so special. And this is what you're going to see, hopefully, if everything goes all right, on the 7th, is the Vikram lander. It's named after Vikram Sarabhai, whose centenary year we are, as you know, celebrating this year. And he was the person who essentially set up India's space program and industry, and to some extent set up India's atomic energy as well. This lander weighs quite a bit, 1.5 tons, and this is the most crucial part of this mission. Landing things on surfaces is not a very easy task. In your lifetime and in my lifetime, I've seen many, many failures. On Mars, for example, more than half of the landers that have been landed actually broke on landing. By many countries, America, Europe, Japan, China. China, the only thing they managed to land broke. And so on the moon, it is by no means there's a 50-50 chance that it's going to actually work. Right? Landing something is very, very difficult, because even if you've chosen the place where it's going to land, the local conditions is very, very important. Yeah, and of course, the right velocities, etc. So the moon actually doesn't have an atmosphere, so you can put it through right to the surface and have it land. India is now planning, as you know, a Venus mission, and there Venus's surface is 700 degrees, and its atmosphere is full of very, very corrosive chemicals, and so there is no way we can actually think of a lander even reaching the surface, and even if it reaches the surface 700 degrees, it's just going to burn up, right? So if the moon does not have that. For Venus, one is thinking of maybe having a drone-like thing that will go up down into the atmosphere as far as it goes, and it burns out, and before it reaches and burns out, it will send us some images. But here, you can actually land things on the surface. This is the first time India is going to try this, and what an apt name for it, Vikram lander. And then, from the lander, the rover is going to come out. First, what will happen is that as it lands, there'll be a lot of dust that will come up, very dusty near the poles. And so one needs for the dust to settle. It will take maybe 3 to 4 hours. And then this little thing, which is only 27 kilograms, yeah, it's lighter than most things you have in your house, tables and chairs, this kind of thing. And it requires about 50 watts of power from its own solar panel. And it's got 6 wheels. I don't know, it looks like a Victorian little, I don't know, 100-year-old little cart that people would take to sell momos or something. I don't know. It looks very unimpressive, but it is fantastic, and I'll tell you in a moment what kind of stuff it has. Right, so it's going to land here. That's what I wanted to show you, the bulk of lunar landings, all these things. I just showed you some of the Apollo landings, but these are the Russian landing sites, Luna. All the American ones are with this flag. They've landed all over the place. Here, the nearest was a NASA mission called Survey, one of the early missions that went to about 40 degrees south. And Chandrayan. So you can see that we're going to land in a completely different part of the moon, right? And that always has surprises. I'm not saying that it'll discover mice coming out of the walls or whatever. That's science fiction. But at least when you go into a completely unexplored part of it's always very exciting. Always very exciting. And the idea is that this is another of ISRO's graphics, just to show what it's going to do. So that's the Vikram is going to open the ramp, and the rover is going to come down, and with its 6 wheels, then the solar panel comes up, like that. All this will happen. And you will see that happen because of this. If you come here, ISRO's speed will show you. This will happen if 1:40, the landing happened in the middle of the night, of course, 1:40 at night. Then this will all happen around 5 o'clock in the morning, and of our morning, that is. And then the rover is going to go around for 14 days of our time, one lunar day, and take a lot of very interesting data. Okay, so that's the whole plan. I just want to show you the difference between what this is doing and what Chandrayan did. Chandrayan was launched by PSLV 11 in 2000, sorry, PSLV 2 in 2008, and it had a weight of about half of what the orbiter weighs. Okay. And it did not, of course, land anything. It went around the moon and it did some really interesting work, but it had very, very tiny instruments. Because of the whole thing, which 1400, and most of it was the satellite itself, there were very stringent conditions that you had to build each instrument, which couldn't be more than a few kilograms each. So they were all built with very fast, but with off-the-shelf things that you could buy from catalogs and stuff like that. And many of these instruments were very, very rudimentary instruments because things were just tried out. Nobody knew whether it was going to ever reach the moon. And even then, it gave some very interesting things. You can see half of these payloads in Chandrayan 1 were from India itself. And out of these, the one that has given us quite a lot of data is a terrain mapping camera. It's a simple camera that mapped some of the terrain and sent us some very good pictures. And there was a lunar laser ranging instrument that actually did some laser ranging to see what's under the surface and also on the surface. Now, there were various other things. And then on Chandrayan 1, there were some payloads that were from abroad. Because a lot of, of course, agencies all around the world wanted to also, because lunar missions are not that common. In fact, even we had a little radiation camera detector sent from the Bulgarian Academy, and there were 2 NASA experiments on it, and 3 ESA experiments on it, European Space Agency experiments on it. And out of that, there was a synthesis aperture radar, which was essentially built in collaboration with NASA, which gave some really good, interesting data. And this was the major outcome that came out of Chandrayan 1, in my opinion. There were many others, very simple experiments that were done to figure out. One of the interesting things that we want to know about the moon is that we know that there is no atmosphere, but actually there is. There is a very thin layer of air, very close to the surface of the moon. And that, we need to know what is in it. We still have incomplete information about what gases there are in that. And so we have some inkling, and one of the major experiments in Chandrayan 2 will do that. But one of the surprises that happened was that with the infrared camera, laser ranging camera, as well as the microwave instrument, there was some when one took images of these surfaces, the thing about the radio cameras, the microwave cameras, is that it can actually penetrate the surface and make you images of what's underneath the surface. Yeah, radio images are not like optical images that we see in the sky with your eyes, but you have to synthesize them later on. Very similar to that black hole image you saw recently, which was actually a radio telescope image. Here you're looking at the evidence of. So what happens is that it looks at how this radiation penetrates the surface of the Earth, and you can map how much it penetrates, and from that, and then comes back, and with the reflectance and the penetration, you can combine the two, and then figure out what's in it, what could cause this kind of reflectance. And as you can see, it was found that the blue bits near the pole of the moon were consistent with water under the surface. Apparently, it's a very large lake under the surface from which the reflectance and the penetration depth combined together gave us some evidence that it could be water. Okay. So this is a very interesting thing that one has found, and this was very close to the pole. And this is why this time we're going back to the pole to find out what's there on the surface, what gases there are near the surface, and whether there's water under the surface. So Chandrayan 2 has now 13 payloads. This time they're all Indian payloads. Actually, there's a little thing that NASA has given us, and I'll show you in a moment. It's very interesting. And these are so in Chandrayan 1 there were these 5 from India and 6 from abroad. This time there were 13 Indian payloads, and this passive experiment. A passive experiment is nothing, but it's not an active experiment. It's something that you go and leave there. You just keep it there, and NASA will then use it. I'll show you in a moment what that is. And so that's a NASA experiment that's going with us. Okay, so some of the very exciting things that are already happening now with Chandrayan 2 as it gets nearer to the moon, and I'll tell you in a moment what it's going to do at the moon, is it started to send us these pictures, and they're very exciting pictures. I showed you one of them. This is an expanded version of these pictures, and you can certainly see these very famous craters. And from these, actually in class, you can do some very interesting experiments by using a ruler. And these pictures, you can actually measure the depth of. So I'm inviting the teachers, if you don't know how to do that, look up Galileo's experiments. Galileo, with a small telescope, actually measured the depths of these craters He actually drew these by hand and measured the depth. And he found a very interesting geometric way to measure the depth of the craters on the moon. And you can do this with these pictures very nicely in class with your students. You can do that. And Galileo's experiments are available very easily on the web and textbooks if you don't know it already. One of the most interesting things for me that Chandrayan 2 has sent back last week is the Shishir Mitra crater. You know, one of the craters on the moon is named after Shishir Mitra. I don't know whether you've heard of Shishir Mitra. We hear about Shukten Bosch, we hear about Meghnath Shah, two famous students of Jagdish Bosch and Presidency College. One of his classmates was Shishir Mitra, who is the father of radio astronomy in India and radio communication. He also was a classmate, as I said, of Bose and Saha, and he went to Germany and got trained in radio communication and radio antenna use. And Ashutosh Mukherjee, who was then in his second term as the Vice Chancellor of Kolkata University, brought him back, just like he brought these amazing people from all over India, like C.V. Raman and A. Radhakrishnan and people like that to Kolkata. Kolkata University brought back Shishir Mitra to Kolkata University, and then he established the first radio sciences department in the country, which is now the Calcutta's Department of Radio Physics and Electronics and Applied Physics. That entire department was set up by Shishir Mitra. So Shishir Mitra, because he was the father of radio astronomy in India, one of the major craters is named after him, and I'm so happy that ISRO made it a priority as Chandrayan is going nearer and near the moon, that it sends us a picture of the Mitra crater. That's Shishir Mitra's crater. Very nice. I like that. Yeah. So I love these pictures that are now coming back, and what you should do is look at ISRO's website, as well as what they do is they first put them on the Twitter feed. ISRO's Twitter feed, if you go to the Twitter feed, every day there's some very nice pictures that are coming in from Chandrayan 2. You can see them. Okay. Now, the plan is then, we started on the 24th of July, and we inserted the Chandrayan 2 orbiter into a lunar orbit on the 14th of August, and I said 0130 hours, but you are now saying 140. Just a hot from the press. ISRO has just this morning given us the exact time of the landing. It's going to be 140 hours. Remember, it's in the middle of the night. And there'll be a live show here, which you'll hear all about. Okay? Payloads, I'm not going to go into all the payloads that are there, but I'll tell you some of the exciting things that Chandrayan 2 is going to do that I think will give us very nice stuff. Why are we going there? Let me tell you first. I mean, what's the whole point of going to the moon, and what kind of science are we expecting? One of the major things that we want to do is to figure out whether we can actually set up bases on the moon. Why do we need that? Because the moon is not that exciting a place, other than the fact that it's the sister of the Earth. I'll come to that in a minute. I'll talk about the origin of the Earth and the moon. We want to know more about how the Earth formed, and the moon is part of that story. It is likely that the moon was formed along with the Earth. At the same time as the Earth formed, the moon formed. There is also, of course, a rival theory which says that moon is part of a fragment of another little planet or planetoid that came and collided with the Earth very early on and left behind this moon. Now, we need to figure out which of these two stories is right. We don't know the answer yet. And by doing experiments on the moon, we can know more about the Earth and the origin of the Earth. That's what I'm trying to say. And that's because we already know from the various samples we brought back from the moon, the moon's surface is very similar to the Earth's surface. The chemical composition of the rock there is very similar to the Earth, apart from the fact that it has evolved in many ways in the 4.5 billion years that both have existed. And so the nature of the rock is different, the chemical composition shows, but there are subtle differences. Differences, for example, that you can dig on the Earth's surface and get to heavy metals very easily. They're near the surface. On the moon you can't. Right? So mining for heavy metals is not that easy on the moon. So there are subtle differences, and we have to probe that. We have to probe and find that. So knowing the moon is very important for us. It's basic curiosity, how did the Earth come to be, and how did we start on the Earth? Why didn't we start on the moon, for example? Life in this part of the universe. That's one basic question. The other question is, we know that in the future history of humans, we will have to leave the planet and go elsewhere. At least some of us will have to. You and I won't. It won't happen in our lifetime. But the human species is getting so big that this planet will be overcrowded. The resources we compete for, at some point we'll have to leave, just like Europeans left Europe and went and colonized us and went into other parts of the Earth which was less populated. We will go into other places of space. We will go there for curiosity as well. We will go there just to show, just like humans climbed Everest, we have to go to other planets and show and test our technological capabilities. All that will happen. But if I, for example, want to go to Mars, to Jupiter, to Saturn, outside the solar system, we can't go in one shot. Even if we devise rockets that can take us directly out to very large distances, you know that if you're traveling from Kolkata to Shantiniketan in a car, you have to stop in at least 3 places to have some tea, go to the bathroom. You need all these stops, right? You need to maybe have some petrol in your car. So going out to space, it has to be done in stages. You need refueling stops. You need places for people to rest for a little while and then go again. So stages have to be built. The first stage will be a space station. The second stage will be a moon, with the moon. Going to Mars, you have to stop at the moon. Go to the bathroom at least. So that kind of stuff. And refueling. So staging is very, very important in interstellar travel, interplanetary travel or whatever. And so we need bases there. So if we want to put a base there, even on the Kolkata Shantiniketan road, you have to put a dhaba there, or you put some shops there. You need to know where that building is going to be, whether people can live there, what kind of robots you want to put there, what kind of resources, and do you want to take all the water from Earth, or is there a lake there that you can just take water from? You want to know whether there are poisonous gases nearby on the surface, so that if you put people there in two years, everybody's dead. Right? You don't want that. So you have to do some reconnaissance. You have to know the chemical composition of everything very, very carefully before you start designing your lunar base. That's the important thing. And for that, every country has to do this. Because it's not that I leave it to the Americans, they will give us the know-how. No. If India needs a base there, like we have a base in Antarctica, we have to do it ourselves. Because it will be part of our space mission. So that toilet will be ours. That fueling station will be ours. It will probably have those odonails hanging there. Right. So all these things are things that are not just what we did in Chandrayan 1. We are going to do a lot more. And very important things I'll just point out to you are Chandrayan 2 atmospheric compositional explorer. This is what I'm talking about. We're talking about the moon having an atmosphere. No, it has a little atmosphere. We need to figure out what the chemical composition of those gases are. Right? We have this imaging IR spectrometer, which is going to, and this is going to be in the orbiter. This is not going to go on the surface. From the orbit, one does analysis, because it's going to be going very close, 100 kilometers from the surface, and it's going to do analysis from the radiation that comes. It also can do ranging by sending radiation and bouncing off the surface. And then one does X-ray spectrometer. So X-rays also are needed because a lot of these chemicals, the molecules and the other things that are part of the atmosphere, we need to analyze their spectrum. Some of them have information in the infrared. Some of them have information in the X-rays under certain conditions. I don't want to go into all that. Okay. And then there is the radio experiment, which is very similar to the Chandrayan 1 experiment that we had, where radio ranging was done by bouncing radio waves from the surface. So these are all the orbiter things, and this will be done from the orbiter. So even if the Vikram lander doesn't work, God forbid, it doesn't work, the orbiter experiments will certainly actually do a lot of these experiments. And then we come to the Vikram payloads. And in Vikram itself, there are payloads, even not on the rover, but on the lander itself. And one of the very, very important things is this. For me, it is the most important thing because it monitors the seismic activity of the moon, earthquakes, not just big earthquakes, but small little earthquakes, the vibrations. We have no idea what it's like near the pole of the moon. There are some measurements that have been done by NASA as well as Russian missions near the equator with seismographs measuring, and we know that there are pretty strong earthquakes on the moon. Right? So if I'm designing a base that's going to be in the moon, maybe near the pole where there's highly likely there is some water, I need to know what is the general vibration there so that I can design my building. Then the thermophysical experiment essentially maps the surface in terms of how hot it is in various places. Very, very important. Because I need to know what the surface is like. Okay? And then looking at the ionosphere, etc. And then on the Pragyan, which is the little six-wheeled Momo car, is going to have actually a very interesting experiment. It's an X-ray spectrometer, which because it's so close to the Earth's surface, is going to monitor the composition of the gases exactly very close to the Earth's surface, as well as the terrain, right? So that's the very important thing. It also has a little laser, which might or might not work, induced spectrometer, which is a riskier instrument, but this is a very, very interesting instrument. And then I told you, along with this, on this particular Pragyan, there is a retroreflector. Okay, where did that go? So NASA, from the very beginning, has sent into space reflectors to be put on the surface of the moon. And we, from the 1960s, have been firing laser beams from the Earth that gets reflected from these. These are mirrors like this. Apollo H took some, Apollo 10, 11, 12, everybody took these and put them on the surface of the moon. And there are 5 different stations now, at least I know of, all over the world, which actually fire these lasers every day, every hour, and get them reflected off those mirrors. And by this timing, you can measure exactly how far the moon is. So we know moon's orbit better than we know most things about ourselves, right? Very, very, for 50 years, we've been looking at how very accurately the moon. Now, one of the things I'll tell you, there are many people out there, including some of my friends who come and tell me, what is the proof that we ever went to the moon? It is all the shot in Hollywood and stuff like that. And one of the things you can tell them is that every hour we shoot a laser that comes back from these things that were left by Apollo on the moon. That is one of the great proofs that we've actually been there. Even if you don't leave a flag there, the flag is not there. But these things are there. And one of these things is going to go on our rover, and it's going to stay there. So after the rover stops roving, NASA's retroreflectors will be there, and we're going to use it for laser ranging for many, many decades to come. So that's the only foreign payload we have on Chandrayan 2 that is going to help us do this, okay? So this is kind of a summary of what's going to happen. And this is why we're so excited that this is going to land. So another question that everybody asks us as we go around is, how can we spend so much money? What is the cost? The cost of this whole thing is less than 1,000 crores, it's about 140 million. And I want you to compare with some of these things. You know, I mean, I loved that cost 2.5 times more than the entire Chandrayan 2 mission. A simple Airbus 320 plane, not even a 380. Airbus 320, the stuff I just took to come from Pune to Kolkata, cost the same as Chandrayan 2. And this is the power of using this low-cost mission to do this very clever building up the orbit, getting to the moon. Okay? The most recent NASA successful lunar mission already cost about 4 times more than this. And it was that Apollo missions, because of the human part of it, cost in those days, in 60s, cost 25 billion put together. So this is nothing compared to the kind of stuff. And what do we get out of it? You can still say that, this is so much more than a couple of Mary biscuits or whatever, ice cream. Why are we using so much money? I can discuss this at length with you, but this makes NASA a superpower in the space industry. We're competing with the private industry now. NASA will make many more times this amount of money by launching other people's satellites once they show they can do this. Right. So it's actually a commercial venture. It is not just an altruistic venture to go and measure and study the moon. NASA is one of the few government agencies in the world who can do this, and already we are launching other people's satellites. We're going to get into the space industry very soon. Okay, so I think finally I want to say one little thing before I stop, and that is the general question of why, as a scientist, I'm excited to go to space and to the moon. And not just this, I can talk about this later, but I sit on NASA's science committee now, and we are now discussing, as scientists, what do we want to do with NASA's missions? Now we have this capability of going up there. And as I told you, we are planning things like Venus, we're planning Gaganyaan, which is taking humans into space, but more importantly, we're planning what science we can do in space. As an astronomer, the first satellite, and I was very loosely involved in it, AstroSat, was launched 4 years ago in 2015, and it's a satellite out there in space, which ISRO launched, but the astronomy community in India built. It has an ultraviolet telescope, 3 X-ray telescope, and an optical telescope, 5 telescopes on the same satellite, looking exactly in the same direction. No other facility in the world does that. And so simultaneously we can observe them all around the electromagnetic spectrum. It's produced some amazing results. And NASA has shown, ISRO has shown, that you can do things as good as NASA. In fact, the ultraviolet telescope on AstroSat is better than anybody has ever built, much better than the best ultraviolet NASA telescope that's been up there. So once we demonstrated that, now ISRO has come to us, the astronomical community, and said, what more can you do? Tell us, and we'll launch it. You build it, we launch it. So last year, the new ISRO chairman actually opened up ISRO to the astronomical community, saying, you give us good ideas, we'll launch it. This is my launcher, you do what. So now we are racking our brains to come up with great ideas what to do, and there are already about 10 to 15 ideas that have come, and NASA is going to go into scientific projects in space, right? With this kind of thing. And so science is very important. Exploring, of course, is you're going to asteroids, you're going to Venus, you're going to Mars, you're going to the moon. Of course, there is NASA. How did NASA start? NASA started as a whole thing after the war to make sure that it can look after its own defense interests by monitoring the rest of the world. And of course, from space, it's much easier. National security is one thing, and of course, India will have to do that at some point. They won't share that information with you and me, but at some point, the Department of Defense and ISRO will work together, and this technology is important. Economics is very important, as you probably know. ISRO already generates a lot of its revenue. It doesn't come from the money we pay as taxes. A lot of resource expenses come from ISRO's own income, and that income comes from supplying weather data, remote sensing data. It will soon have its own GPS network, which will provide phone services to people. So NASA's economics is related to this development of technology, and more the world's community gets confidence in NASA's capabilities, the more you will find, ISRO's capabilities, then you will see that ISRO will get to, because of its low cost missions, it's going to it's going to get to give service to the world. I talked about human destiny. We have to actually eventually get that out there in order to explore the universe. And of course, there's national pride. There's no thing that has this kind of an emotional impact on young people as the capability of going to space. I was in class 2 when humans first landed on the moon, and I remember that changed my life completely. I couldn't think of anything else. I even stopped pasting pictures of cricketers in my book. I started pasting pictures of astronauts in my book. So this is what is very important. It gets people together. It gets people very, very excited about what's happening. Right? So I'll stop there because we're now looking forward to this week, or a little bit more that comes up to the landing of Chandrayan, and there'll be lots of programs here which you'll hear about. But I hope I've been able to give you a little bit of introduction to what's going to happen. Thank you.
Thank you, sir. Sir, with your permission, can we take some questions?
Yes, of course.
Any questions? That lady there.
Yes.
Sir, you know, like Elon Musk, he has his SpaceX, and he says he wants to actually take tourists to the moon here.
Oh, you're here. Good. Yeah, okay. Good.
Like, you know, like how Elon Musk is like saying, I want to take like tourists to the moon, and soon like the super rich will like be able to like fly to the moon. So like, what do you feel? Like, how do you feel about space tourism?
Oh, I'm very excited about it. There are many problems with it. I mean, Elon Musk is a maverick. I follow him. I see what he does. I do not like most of the things he does. But he's a very, very interesting person. But he's opened up this whole idea, right? I mean, Elon Musk is not the first person to talk about space tourism. You know, even Richard Branson talked about it with Virgin and stuff like that. So I think it's inevitable. It's going to happen. As people have that kind of money, they will want to do it. You know, people used to travel in taxis and buses, then they have their own cars, and then they have their own planes, and I mean, there are a large number of people who have their own planes now and stuff like that. So eventually, when the people have the money, they will go up there. Question is, what purpose does it serve? Space tourism, it provides a thrill, but it doesn't serve a much larger purpose. It's entertainment. I am concerned about another aspect of it, and that is, as an astronomer, as a scientist, I'm very concerned about space pollution. I'm concerned about fragments of various things that are left in space. And just as you know, any tourist spot, if you go to a beach, you will see how much detritus is left on the beach. Similarly, a simple satellite leaving lots of little fragments out there is slowly going to make things very, very full. Elon Musk's some other programs are very alarming. For example, he wants, hoardings to be sent into space. He wants all these little satellites with reflectors in space, acting as 40,000 satellites, bringing internet to everybody.
He will like launch his car into space.
He launched the car into space. That was fun. I hope he doesn't do too much of those. But think of me as an astronomer who has a poor little astronomer has a telescope, and I'm trying to see various stars, right? And I built bigger and bigger telescopes. We're spending billions of dollars being the biggest telescopes to look all the way to the end of the universe, to study the universe and things like that. And then all you can see are these satellites and hoardings, and something says Lifebuoy Shaban. Through my telescopes, that's all I see, right? It's like when you travel in the Himalayas and you see the wonderful beauty, and all you see are these big hoardings for selling soap. So that could be a problem. So you have to think about all these. I'm sure an equilibrium will come. All dreams don't get translated into projects because economics comes in, and some sense will prevail. But I think Elon Musk is a maverick, but he's also pretty crazy. So somewhere in between, something will happen.
Thank you, sir.
Yes. Yeah.
Okay, so We're actually all students from the Cambridge School, and we have some very eccentric questions for you, sir. So the thing is, you said something about, how America tried to just propel the rockets it sent directly to the moon instead of going in those circles. So if I assumed it like very normally, it would make me feel like it would crash into something. So the thing is, how do you think their idea is more disadvantageous than ours? Like, for example, we go in those circles, and although it takes longer, it is actually like more secure in that way.
What is really crashing into? Space is a very, very,
No, like, what do you think would be the risk of trying to do it so fast?
No, it just means that the longer you take, if you say that there are more than 100,000 little pieces that are dangerous that can crash into you in space. And that number is growing because they're all traveling at very high speeds and they are all fragments of things that have either exploded in space. I mean, recently India did this, right? They will put up a satellite and then exploded it. And now we have 3,000 pieces that are floating around. So those things, if they hit you at such a speed, they can go right through you and your thing is destroyed. So now, a Saturn rocket propels a satellite that goes to the moon in 4 days. In 4 days, you have less of a chance of hitting one of these things. Now, we catalog most of the large ones. There are many people in the world, including a ex-PhD student of mine, whose job is to sit down every day, look through a telescope and catalog where each of these big pieces are, right? And there's a register kept of all these pieces that are floating up in space so that we know that we can dodge them. But even then, there are much smaller pieces that we don't know of. And so 40 days in space just increases the risk of hitting one of these things. That's the only thing. Other than that, if you look at the flip side of it, and that is saving so much money and also and being able to take much more than you otherwise would have.
Sorry, thank you. I want to ask something.
Okay, right. Mic. He needs a mic. Yes, go ahead. You have the mic. Go on.
So I'm from Ashok, and I want to ask that when the Apollo missions were they were a slingshot from the Earth to the moon. So how did the velocity decrease as a satellite, near the Earth, the moon surface?
So right, these are not just like you throw a cricket ball and you let it go. These are cricket balls with little motors on them, little jet things on them, and gyros on them and things like that, right? So there are little bits of fuel that can be ignited and a jet comes out and you can propel them on the opposite direction, right? And that we can do from here. We can, and it's very, 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 very controlled, and we can do it very precisely, exactly how much we want to turn it and how much we want to give it a velocity, all that can be done there. The gyros, we can control the gyros, the gyroscopes that turn things, as well as then we can fire a little jet to propel it. So that basketball that we throw is not just a passive little thing that's going through there. We can monitor. Of course, there's a finite amount of fuel, and so we need to make sure that you don't run out of it. But so all these maneuvers that are being done, so that you're ensuring that it has the right velocity, it gets there. We did it with Mangalyaan as well. It got captured by Mars, right where it comes. If it has a little bit more velocity, then the moon wouldn't have captured it, right? And it has to have come to that orbit exactly in the right direction. All that we can do from here. By here, I mean from the ISRO tracking station in Bangalore, the ISRAC, and then we can, for Astrosat, I did from my institute, my Ayuka, I have a whole control room in which we control the instruments on Astrosat. And people are sitting there on a computer, we have commands there, and we make sure we move it exactly in the right angle, and then hit a button and it does push. So it goes that way. There was a question, I'll come back to you in a moment.
Sir, I have a query about that retroreflector as a passive experiment set by NASA. Sir, as you told that every day we were sending lasers to that retroreflector, and we are just measuring and interpreting the reflections out of it. So my question is how to specify the retroreflectors. I mean, there are many retroreflectors. Now, how can we specify that on which reflector I want to give my
question? What school are you from?
Satish Chandra Memorial School.
So yeah, good question. The thing is, we of course know exactly where these reflectors are, and now they're in many places. Now we have one near the pole. They're in many places there. The interesting thing is the moon is also moving, right? So, and it takes a while to get to the moon. If you fire a laser, it takes a few seconds to get to the moon. So, and in that time the moon will have moved. So you have to make sure you fire it at an angle that the moon comes exactly there and where that. So you have to calculate all that. And you saw that all these retroreflector arrays are arrays that are made up of small mirrors. And this is the reason for that. It's a little too complicated for your physics right now, but it's to do with the resolution of each mirror and how much. So for example, in order to hit the right mirror at the right time, it has to have not very high resolution. If it has very high resolution, you see what I mean? Then it's much harder to hit the right mirror because it's moving. So that's why these mirrors are small, because the resolution is blurry. So its resolution is very low. So that even if we, within our margin of error, we can still hit that mirror. And that is why instead of putting a very big mirror, you put lots of small mirrors. Each one is a little blurry, right? And so we know which we get. So all these, the coordinates of these things are precisely known, and every day they're updated. And so we know exactly which one we hit, right? And it's a great game. It's like playing a video game, but now with some science in it. And I know people who actually do this for a living, and they love it. Absolutely. Yes. There were questions up there, at the back, somewhere, anywhere? Come back to Ashokhan.
Sure.
Yes.
Sir, I'm from Madhavi Birla Shishmira, and I have a question when you said about those.
Where are you?
No.
There, okay, yes.
Sir, you talked about those like debris, the space debris that it need not be asteroids and all that. However, if there is one pretty nearby the path that they are going to use, the trajectory, however, we can ignore it and still go on. If that happens to break because of some kind of like if it is pretty unstable, so what would happen to the course? Like, do they have anything that they can take some kind of discourse or something?
You're right. What school are you from?
Madhavi Birla Shishmira.
Yeah. So no, actually, if you think of the speeds at which these things are traveling, they're very, very high because they are essentially orbiting the Earth. All of these things are orbiting the Earth. So a satellite speed and the speed of a little tiny screw that has come loose from somewhere and it's traveling on its own, they're the same, and they're traveling at thousands of kilometers per hour. So at that energy, they have destroying power. They can go put a hole in it, and this has happened to a lot of our stuff. In fact, one of the most sophisticated Japanese astronomical satellites, Suzaku, recently, which I was using quite a lot, was destroyed by one of these things. Just got hit, and then we know that the computer was just got fired. And then we looked at the various circumstances and realized a small piece of space debris, which was not in our catalogs, had come and hit it. So you can't do much. You just lose very expensive equipment, and that is why, we are talking of Chandrayan and everything. We're just keeping fingers crossed that actually it goes there without hitting anything. It is now. You can, this has happened to many other satellites that I know, where a gyroscope has been hit by one of the space debris. And you're absolutely right that we build contingencies into things. For example, in order to turn things, we need at least 3 gyroscopes. We often send up things with 6 gyroscopes in them. So if one goes, then we can use another one. Similarly, within some of these instruments, there are contingencies built in, so that if something hits it or something fails because of some electrical surge or whatever, you can't go and repair it there. So then there is some other part of the instrument that can be then reused. They're just booted up, and that can be used, and we can do that from. But in many other cases, what happens is that you just lose communication with them completely, and that's gone. Right now in AstroSat, for example, the ultraviolet camera, there are 2 channels, one of them just went. And I think it was because it was hit by something. And we're using just the other camera. That's life, that's how you use it. So there are many, many dangers in from where you've actually launched it to when it lands and all that happens. If all that happens all right, it is not only because of our engineers, Indian engineers, amazing capabilities, but also sheer luck. Yes, there was a question here. Where are you from?
So I'm Raychaudhury from Chandrayan School, Chandrayan. So I have a question that ISRO is sending lots of satellites and these things in space. But what about the space study? About those black holes and all those cosmological things, which the Western society is also doing with us?
Well, I told you that these are two different things. Launching satellites is one thing that ISRO does very well.
Yeah.
Launching rockets. Now, in order to study black holes, cosmology, astronomy, that's my subject.
Yeah.
And for that you need telescopes and detectors and things like that. And many of these need to go into space because our atmosphere stops most of the radiation that comes from cosmic objects. For example, X-rays, gamma rays, ultraviolet, infrared, nothing comes to the Earth. So in order, I worked for many years in NASA building what is known as the Chandrayan X-ray telescope, which is an X-ray telescope in space. And that's because no X-rays come to the Earth's surface. You have to study black holes, you have to go to space and do that. Right? Now, ISRO's Astrosat is doing that. They're studying neutron stars and black holes through Astrosat. That's the only scientific mission ISRO has in space right now, large scientific mission. Next year, we are about to launch Aditya L1. It's going to study the sun. It's going to be ISRO's second big astro mission. Its camera is being built in my institute, the ultraviolet camera. And there's a spectrometer that's being built in Astrophysics Bangalore. So all that is happening. So these are two parallel streams. ISRO, for the first 40 years, was not quite interested, other than Astrosat, in building scientific missions to do with astronomy. Astronomy and space science are two different things, astrophysics and space science. It was more interested in building launchers and then remote sensing equipment and weather satellites and all that kind of stuff, defense satellites, all that kind of stuff. Now that it has gained this confidence is the whole thing, and capability, now it has come to us, the scientific community, and said, now what do you want to do science? Come on. So now, till now, I've been working with NASA missions and ESA missions and their satellites and their telescopes. I now sit in ISRO headquarters in a committee telling ISRO, now I want to do this. That's the new role ISRO is giving us. Yes. Those two. And somebody will have to tell me when to stop.
I think it will be the last question.
Okay. So there's one more here.
It will be the last question before our former Director General has a question for you.
Okay. Oh, you have it. Okay, I'll come back to you. Yes. Come on.
Sir, I'm from St. Joseph and Mary School. That you said now Aditya 1. Is it like Parker Solar Probe that has been released in 2018 by NASA?
There are two different things. But you're right. Parker is very similar. Parker is also a solar probe. It studies outflows from the sun, and it has gone to also in a place between the Earth and the sun. Studying the sun does not mean that we do the same thing. The sun is very active. The sun has a lot of stuff that is actually, as you know, lets out charged particles, very highly charged particles, and many of that reaches the Earth and causes a lot of stuff happening in our atmosphere, right? And Aditya L1 will be geared towards that, to study the emissions from the sun and how the sun interacts with the Earth. The Parker Solar Probe's emphasis is different. It wants to study the magnetic field on the sun. And some of it is related because it is the magnetic field and the magnetic storms that causes these outflows. So together, there is a lot of synergy between them. But the reason we want, so this will go into what's known as the Lagrangian point. It is the point between the Earth and the sun where you can actually have a spacecraft stationed there. It's one of these places where the true gravitational force is cancelled. So first Lagrangian point, sit there, and you'll sit there because then you can study the sun 24 hours. It doesn't need to be in the Earth's shadow half the time and things like that, right? So does the Parker Solar Probe. It also is also out there to do that. But the missions are slightly different, and of course, there is quite a lot of overlap between what the data that we get. One more question, and then I'll come back to Dr. Mukherjee. Yes. There was one question there. One.
Sir,
Tell me your name and school.
Sir, I am Praveen Mukherjee from St. Joseph Middle School. So I would like to ask that day by day the space deliveries are increasing and they are providing impedance to the space launching programs. So what are what ISRO and other NASA they are doing about the space debris?
Yeah, good point. I mean, it's like people know that there's so much pollution, plastic in the ocean, stuff like that, but nobody's doing much. You started, to tell your fish seller in Jogu Bazar not to sell plastic, whatever. That's the kind of stuff we're doing. That doesn't help anything, right? I mean, I went to the bank ATM the other day. It told me, don't print out your receipt because to save the environment. And yet there were 2 ACs in there, 24 hours, and 3 tube lights. So, people do something, but actually it catches the small fish and don't do the big ones. So, to my knowledge, there is some little things that are being done to sweep up some space debris, not big missions, nobody's interested. Because it costs money, doesn't give you anything. But once a big, NASA mission or a ESA mission, an expensive gets hit by one of those, then people will sit up and say, oh, we'll close those air conditioning machines, stuff like that. It's Abhi.
Thank you for this wonderful lecture. Perhaps the most important achievement of all the missions is to build up our national pride.
Absolutely.
Thank you so much.
The national pride is very, very important.
2 questions actually. One is, I just wanted to know about the innovations that we could achieve through Chandrayan. I mean the spin-offs or anything. Because with that limited launching capacity, limited payload, we have to do those momentum gain through multiple orbital maneuvers. But that surely involves a lot of work on telemetry or accurate calculations at what point we have to fire this engine or that. So the innovation of the spin-off may not be necessarily in terms of the product, but what we have achieved in terms of our practical. This is one. And number 2, how I can find that there is a competition going on. You said something about the NASA achievements. What about China or Japan or Russia? They are also in the field very much. How do you see us in this competition maybe 20 years from now?
So I can't say I'm the biggest expert in the field in answering this, but I can tell you about the spin-offs. NASA, compared to NASA has from the beginning in America concentrated on the scientific aspects of it and spin-offs of it from the very beginning. It was never a closed system. So, for example, as soon as it gained space capability, it opened up the astronomy from space, it opened up physics from space, it opened from biology from space. I'm very proud to say that the person who's in charge of the entire biology experiments from space is ex-Presidency College, Bengali woman, Sharmila Banerjee. And she does amazing experiments, designed these experiments that are taken up by NASA satellites. So all this happened. Whereas ISRO from the very beginning was a very closed system. They didn't trust the outside ISRO community much. And so the technology development that happened with ISRO has not been shared with the scientific community. It has been shared with some industry. It's true, because the industry has built these things for them. But as a result, what they have done is they've gained amazing technology in remote sensing, and as you say, orbit design, and imaging from space. These things have enormous spin-offs. Just like Google Maps have enormous spin-offs now, ISRO can do that kind of imaging with almost the same kind of resolution from space and in multiple bands, and that has spin-offs. The actual remote maneuvering capabilities have enormous spin-offs in the defense industry and many other industries. And they're working with some of the big industries in India already. Larsen & Toubro, Avsarala, big companies which are mechanical companies are working with NASA. And they're using the same technology elsewhere. So I can see that, for example, some of the technology they're learning from ISRO, Larsen & Toubro will use in, for example, building the fusion reactor in France, ITER, which India is a big part of. All that is happening. On a smaller level, NASA has a much, much bigger outreach to industry, building spin-offs and stuff like that, which ISRO hasn't done. Huge. And basic science education, ISRO has nothing. ISRO has no outreach, right? But I can see that the current management, ISRO chief is talking about reaching out to schools, what we can do. This rhetoric has only now started, and I hope something. Otherwise, if you look at the ISRO headquarters, maybe 1 or 2 people are in charge of outreach. NASA has 3 buildings full of people, hundreds of people working on outreach. Look at their website and look at ISRO's website. So that is I forgot what your second question was, but
It's about our place in the competition.
the competition. Yeah, I think what's happening now is that due to government support, China and Russia had quite a lot of their early space industry bloom. And what helped Russia was that the competition with America was very, very important at the beginning. All that has gone away, and Russia really has underfunded its space program quite a lot. So Russia is not that competitive. You can see when it comes to GPS. Now, mobile phones is the biggest industry in the world. And you can see that globally, China is building its own GPS system, America has its GPS system, and India is going to build its own GPS system, right? Once that happens, that's going to be a big money earner. But many of the others are not doing this, and Europe as a whole, ESA, is not going into this kind of launching for other people there. They have the Ariane launcher, right? They have fantastic launchers. The private launching business, the launching capabilities for other satellites is now coming in a big way for this range, and that is because of the following reason. There's a new dimension now, and that is microsats and nanosats. Small little things. Hundreds of Indian engineering colleges and universities, their students are building together nanosats. Now, they can be tested, and these are a few kilograms. These are hands-on exercises that students, undergraduates now can do. Even schools can do. I wish I had that when I was a student. And with the 4,000 kilogram launching capacity, ISRO already did 100 such satellites once, right? And it can do this. I think in the private sector, there will be a huge demand for not launching big things, not launching the Musk's car, but launching small little satellites that have fantastic capabilities, right? To do quite a lot of stuff, even when we go towards asteroid mining or going towards various other things in space. I think that's a niche for ISRO to go into, because you don't need powerful rockets, you don't need space shuttles, you need low power launchers, right? That kind of stuff. So the market is opening up in various different ways, because now, before this, there were few astronauts that would go, and it was national pride, capabilities, showing capabilities, going to Mars, that kind of stuff. Now space is an industry, and you can do quite a lot of very interesting little things in space. And I hope India captures the market for the small scale things first, at the same time developing larger and larger capabilities. That's my answer.
Thank you, Professor Raychaudhury. Somak Babu, thank you. And such was the craze for this lecture, I can tell you. Only we accommodated 14 schools. And during the past 4 days, I don't know how many schools I regretted. Because there simply we cannot accommodate. This is a 250 seat auditorium. So we couldn't accommodate only 250 students. So thank you all the schools for taking part in this lecture. Thank you National Geographic for so kindly sponsoring the refreshments. And just after this lecture, we will be having a quiz program. Those prizes are also sponsored by National Geographic. They are with us for the entire week to facilitate us, to help us in reaching to the people. Thank you, sir. A round of applause for Professor Raychaudhury. Now, two students who will be helping us. I request our former Director General, Sri Ingrid Mukherjee, please to come up the dais, and he will hand over those mementos to Professor Raychaudhury. And I request Madam Risha Tamura, Vice Consul, Japanese Consulate, to please come on the dais and hand over the second memento to Professor Raychaudhury. we recently had our 60 Diamond Jubilee celebration, and this is a memento regarding the Diamond Jubilee. And this is and it will last long.
My request to you,
And there is a volume there, 60 years volume is there.
next time we have a lecture to be organized for principal and people like us. Do it, if possible, inside the auditorium, which has a much bigger.
Sir, will
Ordered by our school.
You should talk to BITM, sir. You should talk to BITM. I am getting BITM.
Okay, very good.